Welcome to Zug. Um, yeah, so over the past year, um, myself, Gav, Vlad, mostly, have been kind of thinking about these various different ideas for how to make scalable blockchains. Like you might recall, originally identified scalability as basically being problem number one in the list of hard problems of cryptocurrency. So then, like back then in March, we kind of identified it as a very hard problem. At that point, it felt to me as though things like sharding and like approaches to actually making things scale should exist, but it was not really clear exactly how to do that, exactly how to solve this problem where if you split things up, then each individual part becomes less secure. And we we had ideas, so we started thinking about it with Vlad. At some point in July, back when he visited Zug, we spent a bunch talking about hub chains, which was this proposal where back then we were still doing proof of work, and you had a bunch of different proof of work chains that were all kind of mined together inside of the same header chain. And if you wanted to move coins around, you'd have to move them from first into the header chain, and then out of the header chain back to whatever destination chain you wanted to move them to. So the two problems back then were, first of all, what if someone creates an invalid block, and spent a few hours thinking about that. Eventually, kind of realized that you can make things work if you assume that all of the data is available. But once you start having data availability problems, that's when it kind of becomes much trickier. And didn't really come up with particularly good solutions back then, except for basically a bunch of heuristics. So after that, meanwhile, at the same time, Gav was kind of building up his ideas, which mostly focused on how exactly these contracts or transaction execution would be able to sort of jump between multiple different substates or shards or spokes or whatever you want to call them. And each of those were kind of developing at the same time. Eventually, at some point in November, we kind of switched to really push it, working harder on developing proof of stake. And proof of stake, surprisingly enough, makes things substantially easier because you can do this thing where you pick a random subset of validators, which you can't do with proof of work because like miners are anonymous, and if you pick a random subset of substates, then whatever the attacker is will just jump to putting all of its power onto those particular substates. So that made things easier, but then the data availability problem still wasn't quite solved. The idea for actually formalizing it and making some kind of really proper document out of scalability only came to me maybe in early March. I was visiting a few universities in February, back at Cornell, Washington, and Stanford, and I just kind of realized that it's really important to give those people some kind of scalability proposal that they can work with, something which clearly makes sense, where all the sort of vague ideas get formalized to a greatest possible extent, and you can see how it sort of works completely from a mathematical standpoint. So started working on the formalism in early March. The way that it ended up evolving actually is that the sort of ideas that I had, the sort of ideas that Vlad had, and the sort of ideas that Gav had just ended up kind of naturally converging closer and closer to each other. So in March I came up with this formalism of affected area and observed area, where the idea basically is that if you have an execution that jumps between a bunch of different substates, then the observed area is the set of substates which it reads, and the affected area is a set of substates which it actually writes to. So the key point that I realized is basically that you can, as long as groups of transactions have disjoint observed areas, you can actually process them completely in parallel. So then I also came up with the revert mechanism, which is actually probably one of the more interesting things, because like figuring out how to revert in a scalable context. So if you find one particular block that turned out to be invalid, and what do? Do you like revert the entire chain? Is there some way in which you sort of revert just that particular one and nothing else? But then what happens if there are messages going between? So the idea here is basically that you figure out a dependency cone of a block. So if you have a block, you figure out which set of substates could have been potentially affected by that block. And if the block turns out to be invalid, then you can just revert the cone without reverting everything else. And somewhere in the depths of the
I think you muted your mic.
No, I haven't muted my mic. I'm just looking. Yeah, somewhere in the depths of page 33, there is this nice sort of pictorial proof that shows how if you just revert the dependency cone, it actually sort of still looks nice. So version 1 came out at the end of March. I spent. I thought it would be finished in a week. I gave it to a couple of people to look at. A very smart guy named Jeff Coleman, based out of Toronto, looked through it. One of the things that we realized is that I'd actually somehow managed to basically forget that the data availability problem was a really big deal, and I kind of sort of just vaguely papered over it, assuming it would somehow magically get solved. And so figuring out how to actually deal with it took about 2 weeks. Eventually, we basically realized that if you're willing to allow a certain degree of altruism and a certain degree of costly altruism, then it's basically fine. But there might be a bunch of tricks that you could use in order to make it just work under completely sort of purely game theoretic assumptions. So fundamental problem here with scale is what I call in the paper called the crying wolf attack, which is basically that problem is that if you as an attacker create a block and you bribe whatever the initial pool of validators is to validate it, then you have what you can do is you can publish just the header, and you cannot publish the rest of the data. Keep the rest of the data to yourself. Now, the block with just the header is invalid because it's unavailable, so theoretically someone should challenge it. Now, in order to prevent challenges from becoming a denial of service vector, challenges have to have some kind of cost, so you can't do too many of them. But then if challenges have a cost, then what the attacker can do is the attacker just keep on releasing these headers, and if the block gets challenged, then just immediately publish the rest of the data, and at that point, basically the challenger will have to, from most of the network's point of view, it'll look like the challenger, hey, look, they just challenged a block that looks to be completely valid. What's wrong with them? So then, so that's, and the idea is that it's as the attacker makes a lot of these sort of fake invalid blocks that actually turn out to be valid, challengers eventually kind of start believing that whenever an invalid block appears, it's just going to be valid eventually, and so they stop challenging, and then the attacker is free to push invalid blocks through. So theoretically, this attack is very expensive. It could cost thousands of validator security deposits. The reason why I really cared about it that much is basically because I really wanted to maintain this sort of complexity theoretic guarantee where if you have, if each node has maximum O of n computational power and he wants to process O of n squared transactions, then I want an attack that knocks down the network to actually cost somewhere on the order of n squared. But this weird crying wolf attack, it only costs O of n. It costs O of n times a very, very large constant factor, but it's still O of n. So it's not. It starts becoming a bigger deal once you start to go into the sort of crazier schemes that try to convert the mechanism from being just n squared to being like n cubed and n to the 4, because once you get to those areas, then the size of each validator deposit will go down to like a couple $1,000s, and at that point, it's maybe your crying wolf attacks will actually work. So then that's still something that we've been coming up with a couple of ideas about. Like, it seems like the whole general field of law and economics has a bunch of fairly brilliant ideas on how to deal with this stuff. How do you actually, basically, how do you punish criminals when the justice system just doesn't have enough eyes to look at absolutely everything, which is basically the exact same problem that we're trying to deal with here. And yeah, I mean, there's a bunch of tricks that worked in this. There's a couple of tricks that worked in the second version that probably will make it into the third. I'm really trying to keep it as simple as possible. Like, you have to balance being between simplicity and effectiveness, because given that the scheme offers a higher degree of scalability, it just has to be more complex. But on the other hand, once you start getting into this sort of territory of really complicated mechanisms that just build things on top of other on top of patches, it's a kind of intuitive sign that either the problem is impossible or there might be some much better solution around the corner. So where I'm at right now basically is that set the paper around. The main sort of comments that I've realized is that it should probably make it much easier to understand. Because like initially this is meant to be targeting a much more sort of mathematician-like audience, but it seems as though most people that are interested in this are probably not the type that are particularly willing to dive deep into symbols and Greek letters and epsilons and so forth. So I'll probably try to change around the style a bit and combine the two, and also sort of do a better job of explaining what each of the individual pieces are for. From an implementation standpoint, like, this is a scaffolding. It seems so far to be a decent scaffolding, but I'm sure there's a bunch of different ways to optimize on it to improve it. So at this point, we're basically we're in the early stages of figuring out kind of what Ethereum 2.0 is going to actually look like from an architectural standpoint. And we'll figure it out, build it around the scaffolding, and then all the little details hopefully shouldn't be too easy to change if we discover some way to make the protocol substantially better, even like 6 months down the line. I would give more of an overview of what our plans are going to Serenity and beyond, although it's at this point probably better to focus more on just getting Frontier out the door.
I'm sure many people are wondering how this proposal ties in with Ethereum. Is this planned to be used in the near future for Ethereum, or?
Yeah, so this is planned to be used for. So we're still deciding on the exact schedule, right? So there's 3 sort of major sets of protocol upgrades that we want to do. One is proof of stake. The other, well, I suppose that's not that major, but a bunch of general things like event trees and patricia tree upgrades and a bunch of like minor protocol stuff that makes life somewhat easier for everyone. Third thing is that we like to revamp the EVM somewhat. The long-term dream is actually basically trying to take as much of the consensus logic as we can and actually stick it inside the virtual machine. So basically, kind of make the client as small as possible and try to have just about all the logic in contracts in some fashion. And of course, scalability. So haven't fully figured out the order of all of those. We're probably thinking that easier stuff will come first and harder stuff will come later, particularly because scalability is something that doesn't just depend on the blockchain protocol. It also depends on things like the thing with scalability, right, is that when you have a scalable protocol, no single node is going to be big enough to store all of the data. So when you're in that kind of position, that you have the problem that like the whole question of data availability, the whole idea of being able to grab data from the network on the fly and being able and doing Merkle proofs and distributed hash table grabs and so forth just becomes much more important. So to some degree, basically getting Whisper and Swarm out is almost a dependency of scalability. Hence why we're kind of pushing that further to the long term.
Great. So as Vitalik mentioned in the beginning, before we started recording, if you have any questions regarding the paper or scalability questions in general, feel free to ask them.
Hi, this is Conrad. My question is, since the observed regions can't overlap inside of a transaction, it seems like people may have to wait multiple transactions before confirming something. Do you expect that if a transaction doesn't jump around a lot between chains, that it will still maintain a quick transaction time of 12 seconds or whatever?
Yeah,
Or do you think that we might be looking at a minute or more for transactions?
that's a good question. So if a transaction it only stays within one substate, then it doesn't really matter what the sort of distribution of the jigsaw puzzle is, because it's going to be in one substate, and whatever block contains that substate will contain it. And so theoretically, you should be able to just get in immediately. If you're jumping around, then yeah, you'll have to basically wait until a block during which whatever part you're jumping around actually appears within one proof. Actually gets included together. So basically, the more substates you jump between, the longer it'll take, and that could easily be an exponential factor. So the general thinking is that like we don't, this whole mechanism is heavily dependent on this idea that transactions are generally only going to interact between at most a couple of substates, and if you're if you're doing the sort of thing where let's say if you have a crowdfunding contract and you have 100 people scattered around the entire state that you will want to say return the funds to, or it's some kind of dividend or whatever, and you generally need to do something that sends something to 200 substates, then I think the solution will have to involve some kind of asynchronicity. So the idea would be, you'd have a sort of routing network built on top of the state, where you'd send your transaction into the routing network, and it would sort of hop from one state to the next as blocks keep getting mined. It will only arrive at its final destination after maybe even potentially like 20 blocks or so. So yeah.
Another question. So have you looked into the issues of, let's say somebody wants to send a transaction that involves two substates that are infrequently used together? Could there ever be a situation where there just isn't any miner or proof of staker that can provide that block, and they kind of get stuck in limbo?
Yeah, and it is an issue. So generally, like as I'm thinking is, like, so fundamentally, I don't, like, I think there's going to have to be, like, transaction senders and dApp builders are going to have to make some kind of compromises. Like, it's not going to be possible to just make a transaction between any two arbitrary substates and expect it to be confirmed within a reasonable period of time. In fact, I think if you actually try to create a system that has that property, you already knock scalability down from n squared to n to the 3 halves. So like, it depends on what kind of transaction it is. Like, if it's something that can be made asynchronous, then you just do it through this sort of routing network, and it'll work fine. If it has to be synchronous, then, like, so one of the things actually that I discovered back when I was talking to Gav about just generally, and then to some of our security auditors about the security of the whole contract mechanism, and is it possible for a child to somehow do some kind of denial of service of a parent? And the thing that we realize is that in pretty much every use case, it's you're either calling a contract that you trust, or you're calling a contract that you don't particularly care about. So if you're calling a contract that you trust, then you know that that contract is going to be in a few particular substates, and you should be able to sort of locate yourself in a place where it's most advantageous. And meanwhile, if you want to send something to some other address that you don't necessarily trust, then you basically rely on asynchronicity in some fashion. And Of course, this is one of those areas where there could be a whole bunch. There's a whole bunch of different strategies, but generally the strategy of trying to sort of make non-essential stuff asynchronous to as much as possible seems like the sanest one. And if that can't be done, and if you're calling something that you do trust, the idea would be that contracts would basically locate themselves close to dApps that they interact with a lot.
So, is your thinking that the addresses of a contract or a transaction will define what substate it's in?
Yeah, pretty much. Yeah, the concept of address might have to change substantially. Like it's at the very least, it'll have to be the address will have to include a substate index. At the most, I could even see some kind of crazy addressing scheme being created, sort of on the high-level language level, where you'd have, if the address is in some particular format, then it's just a normal send. If it's in some other particular format, then it just automatically turns into one of these asynchronous routing things. Mm-hmm.
Well, to ask another question, so let's say somebody manages to sneak an invalid block into the whole system. Is that where this cone of reverting comes into play?
Yes. Yeah.
Okay. And so can you kind of walk through, like, somebody manages to sneak in a bad block? Can you kind of walk through what happens at that point and how that gets resolved?
Okay. Actually, just for visual purposes, page 33 of this of the latest version of the paper is gonna help. But generally, just so if you want to get to that, meanwhile, just give an overview. So, someone creates an invalid block. Just to do a sort of worst-case scenario analysis, we'll assume the data is unavailable. Eventually, a couple of nodes challenge it. Once it gets challenged, then the block enters a sort of purgatory phase, where it could end up actually being valid, or it might potentially be gone and eventually go into the dumpster. So when a block is in purgatory, at that moment immediately, everyone knows that potentially, that block might end up, if you build on top of that substate right now, then your block might end up being reverted. And so the rest of the network has the incentive to sort of temporarily organize around that particular section and try to coordinate off to the greatest possible extent. So meanwhile, while it's in purgatory, either the block turns out to be valid after all, in which case it gets rescued by basically with a much larger sample of people validating it, or the block ends up going through its period in purgatory, and eventually the purgatory period expires, and at that point the block gets reverted. So normally you'd expect the purgatory period to be, 20 or 40 blocks or whatever. But let's, if we suppose that it's something like 2 blocks, then what would happen is that, basically the diagram on page 33, so if you look at the third image, it's if X is the block that's invalid, then the first thing that you do is you would figure out what blocks. The first thing you do is you'd figure out what the blocks are at the next height that are dependent on that block. So dependent on that block basically means that the output of X has some overlap with the input of that block. Then at the height after that, you sort of expand the cone further and you say any block whose inputs overlaps with the output of the previous level is also gets added to the cone. And then you sort of keep on expanding the cone. And hopefully, if the validators are smart, they will have done a good job of sort of coordinating it off, and the cone will eventually basically turn into a cylinder and stay as a cylinder for 40 blocks. And at that point, every single substate root would just get reverted back to the last place where it was before it became part of the cone. So if the particular substate the set of substates that were in the original problematic block, that particular set of substates would just get reverted all the way back to where they were previously. Then if there's some substate that joins in the 10th block, then it would get reverted to where it was where it was before the 10th block, and so forth. And as the diagram shows, the result of doing this kind of reverting actually is still technically valid in the sense that it's still a substate with a bunch of blocks on top of it, except it's just a subset of the original blocks. Did that answer things?
Yes, that was great. Thanks.
Yeah.
I guess just a general question. What is your confidence that, now that you've narrowed down the possible design space for these types of things, that it can be made to work? Is it like 50% confident, 80% confident, or 99% confident?
I'd go with the high end of that range. The mechanism is relatively sound. The things that I'm worried about are more, to what extent can we ensure that, like, to what extent will it actually work well, sort of on the strategy layer. Well, actually, that's one thing that I'm worried about. To what extent will it work on the strategy layer? So, to what extent will the block collators be able to actually, create, like, create these blocks in such a way that a maximally large set of possible transactions can actually work to get included into the blockchain. Like the worst possible outcome would basically be to just have a few thousand substates that almost never interact with each other. And the best possible substate or the best possible thing would be something that actually just acts like a completely generic computer, where anything can happen to anything. So figuring out, like, trying to get things as close to the good end as possible is probably one of the concerns. The other one is just, I guess, a general sort of fragility problem. So networking assumptions sometimes end up failing. The chain ends up getting DDoS some of the time, and what if some kind of DDoS attack might lead to would lead to some invalid block getting in and actually getting in to the point where it sort of survives, where it sort of goes all the way through the grace period and actually gets fully confirmed. So that stuff, I think, will it'll end up depending. So distributed consensus in general relies on networking assumptions, and it's always kind of unclear exactly how accurate they are. How quickly messages can manage to spread. And I've been trying to have decent safety margins for a lot of this. Still trying to figure out how to sort of properly balance between finality and I guess stability, and making sure the scheme works. Mm. Yeah, I mean, I'd say that's probably the largest area where I'm still not fully confident in at this point.
Well, since no one else is asking questions, I'll ask one final question. I noticed in Gav's paper he talks a lot about this concept of fishermen, which seem to be basically validators that don't have a deposit and kind of have a more restricted role. Does that in your design, are all validators?
Okay, so fisherman is basically a synonym for challengers.
Yeah, so you do have challengers that don't have to put forth a deposit. Is that right?
So there is a cost to making a challenge, but yeah, there's no security deposit. There's nothing that you lose. There's nothing you lose beyond the cost for being wrong. And the basic reason behind that is, if you make a challenge, then it's very easy for someone to basically fool the network into thinking that you challenged incorrectly because they just published the rest of the block as soon as you challenged. And so challenging is supposed to be this kind of activity that maybe even might end up being unprofitable 99% of the time, but the other 1% of the time, in order to kind of be a jackpot.
Any other questions?
Actually, the other thing that I forgot to add, the other thing I'm worried about is just generally the sort of constant factors attached to all of this. So like this particular algorithm requires Merkle proofs to get passed around the network, which would increase the size of collations by maybe a factor of 5 or 10. And of course, so that means that it's not really an upgrade from n to n squared. It's more of an upgrade from n to n squared over 10. And then you also got all the extra that have to sign every block. So, if there are any ways to sort of alleviate that particular, some of those constant factors, cut down the Merkle proof sizes and so forth, that's also going to help a lot.
We have a question from T-Soul. He doesn't have a mic, but he's asking in what time frame or stage of development do you think a mobile browser or app can be implemented? I suppose.
Right. So the original plan was for that to happen during the later part of 2015. So the next 9 months. The thing that we've realized is that there's no point in developing light client infrastructure for proof of work because we're getting rid of proof of work. So we'll develop light client infrastructure basically around the same time as proof of stake, because while like the light client infrastructure depends heavily on all of this sort of Swarm and Whisper and DHT stuff, and that's an ongoing project anyway. So we'll probably try to make a light client in parallel with that. The other idea that we actually had is to create a light client that's kind of centralized by default. So instead of using a DHT, basically just use a server which maintains a list of all the hashes of all the objects and like a map of hash to object that it's ever seen, and sort of uses that at least as a stopgap until we manage to decentralize that. So that realistically at this point, I'd say into 2015, early 2016.
Sounds good. Anyone else in the call have a question regarding scalability or Ethereum? It looks like you did an amazing job explaining things.
Yes, Rick. One more question, it seems.
Oh, I see.
Mm-hmm. When will we see these concepts in production? Yeah. Thing is, this is going to take a while. And, we're trying to do it we're trying to do things in stages. We're trying to be realistic about it. So, at this point, the plans, it seems as though we may even end up having sort of 2 major protocol upgrades. So just as we've always meant to have Ethereum 1.1 and Ethereum 2.0. So Ethereum 1.1 it's more modest. It's proof of stake, potentially some EVM upgrades, potentially some of these tree upgrades, and Whisper and Swarm will probably come before Serenity. So that's, but we're hoping by the end of the year. The sort of broader vision of scalability, and particularly of trying to shove as much of the consensus as we can into the EVM. I could easily see that. Very optimistic would be into 2016, and less optimistic would be, well, you can figure out what's less optimistic than end of 2016. $E is the main contender for stablecoins on Ethereum. It seems to be. I mean, the thing with stablecoins is that there's a bunch of these different dimensions in terms of how people would like them to work. Like there's the seigniorage shares versus the positive-negative coin choice. Then there's the choice of interest rate versus claiming mechanism. And it seems as though every stablecoin developer has their own particular take on how those particular things should be done. So $E is by far the most well-developed one that I've seen. I'm sure there's others, like there's always Ethereum projects that are kind of in stealth mode, and then they just eventually come out and announce themselves, and hey, cool, we get yet another dApp. Yeah, so Vid, I was at the $E hangout yesterday. It seems as though they got the interface working, they got all of the basic stuff working. The the main issue that I suppose they might have a hard time doing is just making sure they have enough market makers to make the system work well initially, at least until it gets a lot of users. And hopefully it will. Well, hopefully we'll see 10 different stablecoins get a whole bunch of users, and hopefully at least 2 or 3 of them will encounter some kind of black swan event and fail, so we can learn from it. Transactions per second, yeah. So just doing some quick math. So right now, on average, each transaction takes for Go. Go, I believe, can handle somewhere on the order of 100 transactions a second, and C++ can do quite a bit more. But Go is the main client, and so that's what we have. When we get to O of n squared, so 100 transactions, first of all, that gets up to it gets to about 1,200 transactions a block. When we get to this O of n squared mode, then being able to verify, so that means that it'll be able to verify a few thousand signatures. So it'll probably be able to each block might contain something on the order of, I don't know, 30 or maybe 30 or 40 collations, and hopefully each one of those collations will itself contain a couple hundred transactions. So I'm hoping to get it up to the maybe 3,000 to 10,000 transactions a second rate. At least that that would be fairly ideal. And the nice thing is that because we have quadratic scaling, every single optimization that we can make to a signature verification into the database, we sort of benefit from it quadratically. So if we make everything twice as fast, we get 4 times more throughput. In practice, give it a bit of Moore's law. I don't see any particular reason why we. I'm just trying to think right now. It's it's definitely enough to. So even if we even if we get to just 1,000 transactions a second, assuming Ethereum doesn't get used too often by each user, and say, I don't know, once every 10,000 seconds per user, then that's still that still gives you the ability to handle 10 million active users. If we get to the 10,000 range, then that lets you handle even more. And if we end up going not just to the n squared level, but even to the n cubed level, then that'll get to the point where there definitely should be enough throughput to be able to handle stuff like IoT and name registration and so forth, or IoT and identity, reputation. Just all of the other sort of non-financial stuff that people really care about.
One other quick question related to scalability. I was kind of thinking about the idea where what if you could give proof of stakeholders where you could have a lottery where they would get the right to create an invalid block, but one that in some way isn't damaging to the network, so it's invalid, but you would only know it's invalid by doing the full validation. But if by some chance it accidentally gets onto the main chain or whatever, that it wouldn't do anything horrible. And then basically, if somebody can sneak in this type of block, they would receive some kind of award. And so it would basically be a way of kind of doing code coverage on
Right.
because we were worried that if validation is good enough, there's no one's going to try to spend the time challenging things.
Right. So this is the standard sort of law and economics point that it's not rational to get the crime rate all the way down to 0, because once it's low enough, no one really has the incentive to do that much for deterrence. So one of the approaches that I described in the paper is basically every block randomly choosing one particular substate and trying to validate and see if a particular any challenges on that particular substate are actually legitimate, and if they are, then great. Having having sort of pseudo-invalid blocks go through is an interesting approach. Again, yeah, test coverage is definitely a valuable thing. It lets people see exactly how well the network fares. The other nice thing you could do actually is you can tie it to an incentive system. So you could say that, if a block gets particularly far, then we actually penalize a whole bunch of a whole bunch of top level validators, and that basically creates a sort of private incentive to support to support and subsidize challengers and make sure the whole system works. So yeah, there's a bunch of approaches in that category.
Any other questions in the group?
Okay.
Looks like we had a good session.
Oh, hey, Martin.
Hey, Martin. You, Martin,
Yeah, I think so.
question?
Hello.
Okay. Hello. How's JavaScript coming along?
It's going well. I'm still working on ePash. It's not quite coming out right.
Hmm.
And RPC.
Huh. Just to answer that question, where do I see things in 10 years? I guess, no, you finish first.
Oh, I'm done.
Okay. I think, well, like, to me, I'm getting this kind of impression that, so, once we get to 2.0, I think there's a lot of people that still think that Ethereum is sort of a kind of Bitcoin 2.0 and it's trying to replace Bitcoin. But, when you look at the Ethereum 2.0 protocol by itself, then it actually, I'm not even sure whether it's more similar to Bitcoin or something like Kademlia. Like, it's not even just solving economic problems. It's also at the same time incorporating all these elements of being a distributed hash table to some degree. So, a lot of people sometimes say, well, you don't need a blockchain for this. A distributed hash table is enough. Well, guess what? Blockchains and distributed hash tables may well end up sort of converging into almost the same thing. So, it's I think we're seeing some kind of sort of convergence effect for all these different technologies. Are really seeing greater and greater synergies and working together more and more. So I'm hoping that we'll see some kind of sort of polynomial or exponential effect from that, where like developing decentralized technology just becomes incredibly easy in exactly the same way that centralized technologies are right now. And at that point, we actually will have a magic cloud that everyone can trust.
I don't quite understand how blockchain is like a DHT because
scalable blockchain. So these are the models where only a few hundred nodes actually are involved in any particular substate.
Right.
Yeah. So I'm just saying that there's what really is the difference between a blockchain which ends up using a DHT in order to secure data and a DHT which just happens to have a state root.
A DHT that happens to have a state root.
Yeah.
How would a global DHT have a state root? How would a state root become computated from a DHT?
Using a consensus algorithm.
Okay, so that's the difference between a normal DHT and a DHT with a state root.
Pretty much, yeah. Like it's like basically like in 10 years' time, I'm basically like thinking that these sort of what we call blockchains now are going to turn into these really weird and complicated things that that sort of take a bunch of elements from a whole bunch of things.
Right, yeah. So I haven't totally read the fiber chain redux thing, but I read most of your paper on blockchain's scalability, where we're trying to find subspaces. How exactly do you find a subspace or the affected area of a given contract?
So it's not an affected area of a contract, right? It's an affected area of a transaction. So subspaces, you can think, I mean, subspaces are just basically a way of dividing virtual land, right? So if you think of the address space as being virtual land, you just pick whatever subdivision you want and you use it. The way that you figure out the observed and affected areas is basically you just sort of follow the stack trace, and whatever the stack trace ends up being, or ends up reading and writing to, you just keep a record of that. As far as translating the scalability paper into Italian, maybe wait a little, because I actually am going to release a third version, and that's probably going to include a bunch more words in it, because people seem to like English much more than Sigma plus Beta. You know, I'll have the Sigma plus Beta, but I'll probably have both.
Yeah. Make everybody happy.
Yeah, exactly. And then the book will be 100 pages.
Yay.
Oh, yeah.
Probably Leonardo wasn't that happy when he heard like 100 pages.
No, I mean, the extra 55 pages will be much closer to normal English and not so much math speak. So.
By the way, speaking of translations, how do you recommend to treat some of the terms when translating from one language to the other? Like, it has been a discussion.
Right. Like, what kind of term specifically? Because each term has its own story to some degree.
Yeah, well, starting from blockchain to contract, smart contract.
Right. Okay, so blockchain, I mean, I think it's fine as blockchain. You know, whatever the word for block is, whatever the word for chain is. That's, now contract, you know, one of the points that I've been making lately is that the term contract is just a really bad choice initially, because like Ethereum was originally just meant to be a system for people to make Turing-complete derivatives with each other. So it's like back then contract really made sense, but now contracts are more like sort of autonomous objects. I don't know, like there's some computer science term that should be good for them, and if your particular local Ethereum community does not yet have a word for contract, maybe consider, taking the initiative and coming up with something that doesn't have the implication that it's trying to replace the legal system. Terms coined in the context of Ethereum should remain in English. I mean, the thing is that different languages have different conventions for that. Like, yeah, DApp, I suppose, probably. I think like some more European languages tend to not have a problem with just importing English words in a bunch of ways. Meanwhile, Chinese seems to prefer translating everything literally into whatever the words are that it had before. So that's basically try to, I guess, follow similar conventions to what have been followed for the internet. Most important piece of the Ethereum documentation to translate. White paper, the 1.0 white paper probably. Tutorials probably the next. Like, people get the white paper and they get tutorials. It's, probably the highest value that you can get in terms of people being able to understand Ethereum. Do you have lots of room at HQ for all the beer empties? Well, the house that we have in Switzerland is, it has space in it. Yeah. Yeah, house is pretty scalable. Not quite O of n squared though.
Hey, how's light clients gonna work with this fiber chain stuff? Is it gonna work the same way?
Pretty
Like
much, yeah.
you'll just download, you'll pick like
So
what
there's
states are
two levels
interested
of
in.
right.
Oh,
Okay,
sorry.
so there's two levels of light clients actually, right? So the first level of light client is that is the sort of light client that does where all it does is it just validates the consensus. So in the case of proof of work, it just checks block headers. In the case of proof of stake, it'll like jump through and check validator signatures. So in that case, you do the same thing, right? You check the validators. You just jump through the super blocks. You check validator signatures, and
Mm-hmm.
when you figure out that a particular block is valid, then you have the state root. From that state root, you can figure out all the substate roots. From the substate roots, you can figure out whatever part of the state you want.
Right.
The second and sort of harder part of being a light client is this idea of collaborative validation, where you check that some particular transaction was implemented correctly. With that, I mean, it depends. I'm actually even still debating whether or not it's particularly worth supporting that. Like, it was very important back for 1.0 because it was sort of designed around the assumption the state will eventually be 10 terabytes, and so you have to be. It sort of becomes really important to protect yourself. But when you, but once it becomes scalable, then hopefully every single Ethereum instance will run with like under a gigabyte of total state information, and so it'll just there might not even be much of a need for collaborative validation anymore. So that might make light client's job much easier.
Yeah, that's
Um,
actually that's an interesting point because it's like it's another way of saying scalability is like almost all the clients are kind of like light
right.
clients now.
Yeah. Actually, yeah, it's interesting that if you take this scheme and you stack it on top of itself infinitely, then the load of any particular node becomes logarithmic. So, yeah.
Right. That's a really good property having a system too, where like it can scale to be like a light client, or it can scale to be a node, all within the same
Yeah.
protocol.
Yeah, you can choose to be a node. You can choose to have multiple substates. I mean, potentially the equivalent of blockchain.info, which I guess for us is EtherGit, is probably going to end up just storing the entire state, even if when it goes scalable and it ends up being 2 petabytes.
Right.
Just because they can. Um, any estimate on a DevConf date? It's been in a couple of months for a couple of months now. I think maybe wait until after Frontier launches before figuring out any sort of dates for anything else, because at this point we're just focusing so heavily on Frontier. Or at least those of us that are at least those of us that are critical path for Frontier. The thing is that Frontier, like Jeff's really much more critical path than the rest of us at this point, and so there's to some degree, we do have time to sort of get 2.0 figured out at the same time. Location, this one probably going to be Zug or Zurich. Toronto, yeah, I mean we'll definitely consider Toronto maybe for a third. Yeah, you forgot Asia. Asia's important. And Antarctica. ETH Antarctica 2018, go, go, go. Hmm. I mean, I guess the fossil industry is doing a good job of decentralizing that particular iceberg already, but yeah, that's a pretty fun network latency. Yeah, I guess Moon isn't that bad. It's more Mars that's the issue.
Moon 2050 sounds like a sci-fi movie.
Yeah, I don't know if the 12-second block times would work on Mars.
Yeah, no. No. I
No.
was thinking for a second that there might be some really clever way to make it work with with quantum entanglement, but no. Well, actually, the thing that you could do is you could try to come up with some mechanism for having the two sort of chains cross-reinforce each other in some weird fashion in the long term, so it's a 12-second block time within the point from the point of view of each planet, but then it ends up, but then it kind of slowly converges, so gets cross-consensus together over time. Yeah, correct. You can't transfer information with quantum entanglement. Well, the nice thing that quantum entanglement does give you is a shared source of randomness, which actually is one of the more annoying problems in consensus. So if we can rely on every validator having the same entangled particle, then that's might actually make things quite convenient.
How so? Didn't they just have the same randomness?
Yeah. So the idea would be is that let's say the randomness would be used to figure out who the block proposer is. Then you don't need any kind of like NXT style algorithms to figure that out. It just sort of happens.
Yeah, that'd be really cool.
Yeah. Actually, the benefit of that is that would basically sort of replicate the way the proof of work works to almost a complete degree.
Right.
Yeah.
So quantum entanglement for Ethereum 3.0?
Yeah. Quantum entanglement, right. Hopefully that's, hopefully we'll get quantum computers for a while just because they make a lot of cryptographic stuff work less nicely. But, on the other hand, they'll make a whole bunch of AI problems much easier, so maybe they'll make the singularity happen faster, maybe that's fine. We'll just have to suck it up and switch to Lamport signatures.
And how big are Lamport signatures? Aren't they still huge or something?
So there's a few variants. There's the default Lamport signature, which I recall being on the order of like, at a 256-bit security level, like 8 or 16 kilobytes. There is Carl Gluck's hash ladder variant, which goes down to 1 kilobyte. But then both of those are one-time use signatures. If you want to turn those into an n-time use signature, then for every bit in the logarithm of n, you add 32 bytes. But the problem with n-time signatures is that you still have to like prepare the you have to kind of prepare the signature data, and like it takes O of n time to prepare yourself for n signatures. There is actually a signature scheme that's really clever that manages to get rid of the whole n time thing. It's like it's infinite use. It uses this weird concept of a binary certification tree, where basically the idea is that you take your message, then you hash it, you hash it, then based on the hash, you sort of based on the first bit of the hash, you sign either 0 or you pre-generate. So you have some deterministic algorithm for pre-generating a key at 0 and a key at 1, and then you use a 2-time signature. And with your 2-time signature, you either sign the message for 0 with the 0 key, or the message for 1, or the message for 1 with the 1 key. And then either the message for 0 or the message for 1 is itself a new key. And then you build out of that another binary certification tree, and you sign, and you sort of keep on descending. So it's really cool. The problem with the algorithm is that it's even bulkier. So one of these signatures at a 256-bit security margin takes up 41 kilobytes.
Oh, yeah.
Now I'm trying to see if there's some clever way to knock it down from O of n cubed to O of n squared, but I don't know.
Yeah, it's not like a very pressing problem yet. So.
Yeah, I suppose. Hopefully computers will also be much, much faster by then.
Right.
So do we have any other questions or topics to debate, or should we end this session and save for next one? Oh, Yuri seems to have one.
I think, as I've said, theoretically up to 100 or so. Yeah, up to 100 or so, I think would be a good answer. In practice, it'll end up being much less. Yeah, so the theoretical limit from the gas is about 145 or so. From the limit from a computational standpoint is about 120 or so. So, in that ballpark. As I've said, hopefully by a factor of by a factor of 100 or so. But, yeah. Potentially, maybe if we do a bunch of optimizations, that could go up to up another order of magnitude, but we'll see. Okay.
Yeah. Thanks for everything, Vitalik. Awesome session. I'm glad we recorded all this stuff, so other people can catch up. So thanks again, and thanks everyone who joined the call.
Yep, sure. Leonardo, go ahead.
Okay, bye-bye.